So far, we've talked a lot about how wires feel magnetic fields and also how they make magnetic fields. Now we are going to see two applications, the motor and the generator. Before we begin, we need to review the concept of torque. A force is a push or a pull on an object. If the object is free to move and the force passes through the center of mass, the object will accelerate. But if an object is hinged at a point, the force would cause the object to spin, or more correctly, it would change the rate of spin. It would cause angular acceleration. In this case, we wouldn't call this a force anymore. We would call it a torque. Forces make things accelerate. Torques change the rate of spin. They cause angular acceleration. Torque is also calculated differently from force. When you open a door, you're causing it to rotate around its hinges. But practically, you always push the door on the jam side, never on the hinge side. That's because when you're making an object spin, like a door on its hinges, the placement of the force matters. The further the force is exerted from the hinges, the easier it is to spin. The distance from the hinges to the point where the force is exerted is called the lever arm. It is symbolized by the letter R, and it is a vector. Torque has to account for both the strength and location of the force relative to the hinge. The calculation is as follows. Take the cross product of the lever arm, that's the distance from the force to the hinge, and the force. That is, take the size of the lever arm, multiply by the size of the force, and then multiply that by the sine of the angle between them. Torques, like any other cross product, have direction. To keep it simple, we will say that a torque that tends to produce counterclockwise acceleration is positive. A torque that produces clockwise acceleration is negative. A motor consists of a square of wire attached to a shaft, shown here as a gray circle. This is connected to a circuit and placed in a magnetic field. When you turn the circuit on, a current will flow. Now, since you have a current flowing in a magnetic field, the wire will feel a force. As we saw before, the force on a current-carrying wire is given by IL cross B. The magnitude of the force is given by I times L times B times the sine of the angle between L and B. And the direction is given by the first right-hand rule, the one for forces on wires. In this visualization, the current in the far wire, the left wire, is traveling in the positive Z direction. The B field is in negative X, so by the first right-hand rule, we get a force that is in the negative Y direction. The wire is going to feel a force pushing it down. But hang on, the wire is hinged at the shaft, while the force is at the wire some distance away. So this force is really a torque. Let's calculate the torque. The distance from the location of the force to the hinge, aka the lever arm, is the width of the side divided by 2. So it's half the side width of the wire. I won't go through the full derivation, but by plugging in the distance from the shaft to the wire, that's W over 2, and the force on the wire, which we calculated earlier, we end up with the torque. The size of the torque is the current multiplied by half the area of the loop multiplied by the magnetic field. From this visualization, we can also see that the torque is counterclockwise. Now, to get the full torque, we have to double this value, because there's a wire on the right side feeling a similar counterclockwise torque. This yields the maximum torque of the motor. The uppercase N in this equation represents the number of loops present in the wire. A motor contains a current-carrying wire that feels forces from magnets, but because they are hinged, rather than moving, they spin. An electric generator has a similar setup to a motor, but instead of using a current to rotate a loop of wire, it uses the rotation of a loop of wire to produce the current. Here, we see a wire face on to the magnetic field. What would happen if we rotated it? The answer is that the orientation of the loop of wire would change, and since the magnetic flux through the loop depends on the orientation of the wire, the magnetic flux through the loop will also change. Now, according to Faraday lens, when the magnetic flux changes, a current and a voltage develop in the wire. The voltage depends on the rate at which the flux is changing. That's delta phi over T. Since the size of the magnetic field and the area of the loop are constant, that means the only factor that affects the rate of change of flux is the rate at which the coil is rotating, its angular velocity. In rotational kinematics, the symbol for angular velocity is the lowercase Greek letter omega. Rotational velocity is usually measured in radians per second. Radians are a unit of angle measurement, like degrees. A radian is about 57 degrees. Anyway, angular velocity times time gives you angle of rotation, and we can plug this into Faraday's law. The full derivation from this point onwards requires some calculus, so I'll just jump to the punchline. The voltage that develops in the loop is given by this equation at bottom. It depends on the number of turns, the strength of the B field, and the area of the loop, all of which are constant. But it also depends on the sign of omega t. The voltage depends on time, which means it is changing with time. In fact, if you were to plot the voltage over time, it would look like this. The voltage starts at 0 when the wire is face on, rises to its maximum value when the wire is edge on, and then falls back to 0 when it becomes face on again. But then something fascinating happens. The voltage becomes negative. What does that mean? It means that the current will travel in the opposite direction. And this is exactly what happens until the wire completes the cycle and reaches its original orientation. And then the process starts all over again. An electrical generator produces alternating current. Unlike a battery, which supplies a consistent voltage, in alternating current, the voltage varies between positive and negative values sinusoidally. So the current keeps reaching a consistent maximum value, dropping to 0, and then reversing direction. The number of cycles per second is called the frequency. In the US, that's 60 cycles per second for mains voltage, or 60 Hertz. This video introduced the operating principles of a motor and a generator and the concept of alternating current. We will explore AC more in later videos.